Hi everyone, good morning guys. Good morning. So let's begin the class. I am sharing my screen. Okay. Yes. Uh, so far we have discussed about a few deep learning models, right? And now we have to discuss about auto encoder deep learning model, which is auto encoder deep learning model. Before that, since PCA is not covered for many of you guys, I will actually explain PCA first, which is under actually machine learning model. After I explain PCA, then we will go to auto encoder topic, which is under deep learning, right? Okay. So let me begin, guys. Yeah. PCA stands for Principal Component Analysis. Okay, Principal Component Analysis, which is actually used for dimensionality reduction problem. Dimensionality reduction. It is used for dimensionality reduction, right? And we need to understand why do we have to reduce the dimensions in the first place. Okay, so let us see if there are too many dimensions. Is it always a good thing? Okay, is it always good to have too many features? So let's say I have a tabular data where I have to predict y and I have x1, x2, x3, x4, right? And I'm giving more information. Let us say after few days, I will give you more features. X5, X6, X7 also I give, right? Using these and these, I can predict y as much accurately as possible. Okay, initially I had only 4 input features. Later I got more data and I gave 3 more input features. Okay, so in that case, can you tell me, is it good to have many features so that whatever y we predict, it will be more accurate?
Yeah,
What
it
do
is
you
good to have.
It is good to have. Okay. Any other answers?
No, it's not good to have many features.
No,
I
it's not
also
good.
know.
Okay. Why do you think it is not good, or why do you think it is good? If it is good, then why? If it is not good, then why?
I mean,
If it is,
there are too many features and there is no new information being captured. It would
Hmm.
unnecessarily increase the cost of model and time of model.
Hmm. Hmm. Right. Okay.
So as long as there are as many features as the enough information is captured, that should be enough.
Okay. Okay. All right. Fine.
If
If
you're having the,
hmm,
some features and if the accuracy is less,
hmm,
adding more features would definitely make the model better when compared to accuracy. It doesn't mean like we should not have many features. We can have, but like if there is, we need to check for the multicollinearity as well. If there is a multicollinearity, then we have to reduce the number of
hmm.
features. That is what I feel.
Okay. Okay. Right. So it can be good if the new
Hmm.
features are actually giving some new information through which you are getting better accuracy, and there is no multicollinearity.
Yeah, exactly.
Yes, and the newly added features may not be that useful if there is multicollinearity, or if, let us say, the features are not at all relevant. For example, I have features like roll number, index, name of the person. Those are not relevant in any kind of predictions generally, right? So adding that will only actually increase the overfit problem. So the answer is yes, you both are right. Everybody is right over here. It is not always, it totally depends. It totally depends upon the situation. Having many features is not always a good thing. right? Because many features can be correlated, just like the multicollinearity point, and many features may be unimportant. Right? For example, I may add roll number of a student or employee ID. How does employee ID decide, let's say, the performance of the employee? It does not, right? The skills, the hard work, the experience he has put, that depends. If that information is there as inputs, it is good. But if I add employee ID as new information, it is irrelevant information, unimportant information. So that will not increase the accuracy overall. It will only make the model overfit in the trained data. Okay. And last is, it is tough to handle if there are too many input features. So if I have 10 input features, 15 input features, it's fine. But what if I have 70 input features and one input feature Y? Or what if I have 170 input features or 200 input features? Right? Can you tell any classical machine learning models? Let's say, let's just write over here. In machine learning, classical machine learning models, we have linear regression, logistic regression, decision tree, random forest, uh, ADA boost, XGBoost, gradient boosting machine. Like this, we have many, right? K-means. Okay, first, name base also. So these are all classical machine learning. I'm not talking about deep learning, no neural network model, right? If for these models, can you tell which model will be capable of dealing 200 input features? Can linear regression deal with 200 input features?
No.
Definitely no.
No.
Multicollinearity will
Hmm.
happen. I feel
Multiple.
decision tree,
Okay, decision tree maybe, or
KNN.
XGBoost we can say.
No.
Oh,
And
yeah.
then yeah. So still there is no straightforward confident answer that yes, this will be able to deal with 200 features or 300 features or 500 features, right? So that is also one big issue, right? That is, if there are too many features, it's too tough to handle, and we cannot process the understand the data also in the first place. If we have 10 features, then we can look at the table and understand first how is the data. If we have 200 features, then it's difficult to understand for us also, and it's too difficult to handle. And apart from all of this, one big reason why it is not always good is curse of dimensionality. Curse of dimensionality. Yes, these are correct reasons. Multicollinearity, unimportant features, too difficult to handle. All these are correct answers. But this is also a correct answer, which is a bigger reason why too many features is not good is because of curse of dimensionality. What is curse of dimensionality? Let us understand. Okay. So if I have the data where I have multiple features like this, okay, then let us say this is how the data is spread. Number of records. Number of features are, let's say, 15 or 20 or whatever. And I have number of records like this. Now what happens is, when the number of features increase, that is the dimensions increase like this, right? Initially there were only 4. Then I have added 3 more, let's say. Okay, the dimensions increased. So the sparsity will increase. Non-linearity will increase. Variance of the data will increase, because it's the first thing to understand. Variance of the data will increase. Okay. So now if I show you, yeah, look at this, guys. Initially, only 2 features are there. Data is like this. Very tightly packed, compact. Variance is less. 2 more features have added, x3, x4. Now data is this within the 4 dimensions. Now you see the data is not tightly packed like this, right? It has changed. Data is little spread. Data is little spread. which means variance increased. Variance of the data increased. Okay. When the variance of the data increases, do I need a simple model or do I need a complex model to capture the data pattern?
Complex model to capture the data pattern.
Yes. So here a linear model is good enough. But here, if I have linear model, so much of error is there. Here the error is less. No problem. Here error is very high. So does not work. I need something like this or whatever it is, whatever kind of a linear model, non-linear model, I think. Okay, so something like this I need. This linear model won't work. Linear model will have, as you can see, high error. Okay, so we need to have a non-linear model. But we all know finding non-linear model, finding a curve like this is more difficult than finding a straight line. Yeah. Tell me any linear model and non-linear model, guys.
Linear model is like you need an example or the
Yes, in machine learning models, whatever you have.
linear regression.
Linear regression.
Yeah. And non-linear model, let's say XGBoost or ANN.
Logistic.
No, logistic is also
Logistic
linear.
is also non-linear only, right? Yeah, non-linear, right? Kanika?
No, logistic is linear. I will tell that why. If you don't know, I'll tell that why.
Okay.
Where are we? Yeah. So linear model is linear regression. This you can see. It's a simple model. We all know that. Let's say ANN. ANN with activation functions. Is it linear or non-linear?
Non-linear.
Yeah, with activation functions, non-linear, right?
Yeah.
So ANN implementation, coming up with ANN is much tougher. As you can see, yesterday, in the last class, we have seen 100 epochs we ran, 50 epochs, 10 epochs we ran, right? Which batch, mini batch gradient descent, Adam gradient descent. Okay, so it's difficult. It takes more time to find a good ANN model with so many epochs. But linear regression with 10, 15 iterations overall, we can easily find on a very limited this thing. Okay, it's easy. So this is also a problem. The curse of dimensionality is this only. The curse of dimensionality, curse of having too many dimensions is this. That is, variance will increase. Variance will increase. When the variance increases, naturally we need non-linear model, right? Naturally we need very complex non-linear model. But finding such a complex nonlinear model is difficult. Okay, that is why it is called as a indirectly it's a curse to have so many dimensions. Right? We may think it is good if we have if in a tabular data. We may think if we have the tabular data. If we have as many input features, it is good because we will have more information. X1, X2 until Xn. Okay, we will feel it is good and assume there is no multicollinearity and no unimportant or irrelevant features. Okay, everything is important and everything is not correlated. Okay, guys, can you mute yourself? Somebody is okay. So in that way, we will think that it is good actually to have many features because every feature will give some information because of which we can predict y little bit better. Yes, that is true, provided we come up with a model which actually learns everything from the input and the output relationship across these many dimensions, n dimensions. For that, we need definitely a non-linear model. Okay, so I'm not saying it is difficult in these days. These days, it is very easy. These days, it is easy to deal with many features. Okay. But when PCA was invented, it was in the 1900s, right? Around 1930s, 1940s, 50s, around that time, people were trying out for some alternatives like this, when even the computational power was not that great. Computation power was not that great. Right now, we have GPUs and LPUs, TPUs, which can actually build deep learning models much faster. So right now we don't have any problem of dealing with many features, right? Yes, it is comparatively difficult to come up with a non-linear model than a linear model. That is always the case. It is little bit more complex, obviously, but it is not uh, a problem anymore, right? But in the early 1950s, around that time, there was no computational power, right? Therefore, people did not have enough resources to actually run so many epochs and lots of mini batch gradient descent and all of these things uh, to come up with a non-linear model. So people used to look for alternatives. That is, they wanted to reduce the dimensions from 4 to 2, or from 40 dimensions to 5 dimensions. Right? If I have more dimensions, they wanted to somehow transform the data into lesser number of dimensions and still have the same data representation as much as possible. Okay. When you compress the data, there will be some data loss generally, right?
Yes.
Yeah, but they will try to get as much data representation as possible. Okay, now let's see one small example here, why the variance increases. Why the variance increases. So here I have 2 dimension, 2 points. 1 comma 2 is 1 point, 4 comma 6 is 1 point. Let us say I will add 2 more dimensions. Before that, let's see what is the distance between these both. Distance between these both is 5. Distance between these 2 points is 5. Okay. Now I will add 2 more dimensions, x3, x4. I added x3, x4 for this point. So 1 comma 2 already whatever is there, that will be there for x1, x2. It will be same. x1, x2, 1 comma 2 is same. Okay. x3 is 5 for this point. x4 is 7 for this point. Okay. Similarly, for this point, x1, x2 same. x3, x4 is 50 and 10. Okay. Now, if you calculate the distance between these both, turns out it is 45.37, like approximately you can see. So did the distance between the 2 points increase after adding the dimensions?
Yeah.
New dimensions, it got increased, right? So I just showed for 2 points over here. Imagine you have, sorry, 100 records, so 100 points, and all of that will be like spread very vastly like this. Here, this is the variance. Now here, suddenly this is the variance. So you need a very complex nonlinear model to be able to capture the data pattern. Okay, clear guys, why the variance will increase as you add more dimensions?
Yeah, clear.
Okay.
Mani,
So
just to check, when you're putting its more dimension, the
yeah,
distance has increased. That's interesting.
yes. Yeah, you just see the distance between these both Euclidean distance, you can see. This already you have this 9 plus 16. And from the third dimension, this is what is the new distance. Fourth dimension, this is the new distance. The total is 45. This one. Right. See, when will it not increase? When x3 is 0, x4 is 0, x3 is 0, x4 is 0. Then it will be same, obviously. But when I'm adding a new dimension, it will almost never be 0, right? When I add a new dimension, some information will be there about the dimension. Let us say this is let's say this is experience and this is a skill score. This is his previous loan credit score. I'm adding previous loan credit score. So something I will add when obviously the distance will increase overall. Right? Are you able to understand? If you
Okay.
this is as per simple as per Euclidean distance. Euclidean distance is what?
No, that's what I was coming to. See, there's in the Eulerian distance, if a point is defined in a space and you increase the dimensions, yeah, correct. That's how it happens.
Yeah, it will increase, right? Because so far these two dimensions I had. Now I added more dimensions, so distance will become plus 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 always if I increase more, right? In each dimension, so it will increase overall. Always it will increase. If I add more dimension, sorry, if I add more dimensions, it will increase even more. It will go even beyond 45 between these 2 points. So as you provide more and more features, more and more information, distance between the points will increase, variance will increase, right? Yes, you're giving more information, which means you're giving more new information. If you give more new information, one second. If you give more new information from each feature, variance will always increase because you're giving some information. So another variety of uh, dimension information will be captured through which y is changing, right? So variance will always increase, which is a good thing in a way, but bad thing in a way, because if we want to deal with simple models, then they can fail. When you deal with complex models, no problem. It's always good thing to have many features, right? So that's why the answer is we cannot tell is it good to have many features. I cannot tell good or bad always. Okay, I can only tell it depends upon what kind of features you're adding. If you're adding multi-collinear features, then they're not good. If I'm adding new features and I'm allowed to use ANN model, it's good. Okay, right. So this is the curse of dimensionality, right? Which is you increase the dimensions, the spread of the data will increase. Therefore, the non-linear pattern will increase. Non-linearity will increase. That is the distance between the points will increase. Therefore, it is difficult to come up with a model that can capture the non-linear pattern present. Right? Again, this is in 1950s. Okay, you have to learn everything with respect to a context. Right? If you say like this now, people will say, "What are you talking? All the LLMs are complex models. They are building every week one new LLM is coming. So you can't tell that non-linear pattern capturing is difficult now. It is not. It is as per 1950s, as per the PCA, why PCA model was built because of this issue, in 1950s, right? Okay. So I think so far curse of dimensionality is clearly understood. Now let's go to PCA intuition. Okay. Okay. So I have many dimensions. I want to reduce it. I want to reduce the dimensions, which I can do using principal component analysis. What are principal components? Principal components are new features. These are new features. Okay, which are linear combination of original features. Linear combination of original features. Okay. Okay, guys. Before I explain PCA, should I tell why logistic regression is linear model?
Yeah, please.
Otherwise, we will miss the chain of thought. Okay, so fine. So let's see the linear regression. This is a linear model, very clear. Okay. Logistic regression. Why do you think it is non-linear model? Because you imagining this S-shaped curve? Yeah.
Yeah, activation functions.
Okay. Okay. Right. That is correct. Let's see. See here. So W0, W1. One second. Sigmoid is with respect to the here. What is this Y here? Okay, this is Y, right? This is X1, X2. We know this. What is this here?
Probability.
No.
Yeah,
Probability.
probability.
It's probability. Okay, and also let's see. 1 second. Logistic regression, sigmoid. Yeah, you can take it as X itself, for example. Okay. Yeah. So let's have a look at the sigmoid that we will use. 1 by 1 plus e power minus
Minus
y minus y hat. Yeah, this is what is the sigmoid that we will use in logistic regression, right?
Yeah.
So that one, if you further expand, we will assume that y hat is this one only. This one only we will assume. Copy this. Right. So all we are trying to do is in logistic regression, essentially what we are trying to do is somehow take the linear regression prediction and transfer the results between 0 to 1 so that this will act as probability, and using a threshold you can say whether the prediction is class 0 or class 1. That is what we are doing in logistic regression, right? We will take a linear regression model only, which is this. We will assume this is the relationship between input and output. Fine. Okay. So for given these weights and these input features, you will get certain y. How to convert this between 0 to 1 is using sigmoid. We will use this simple formula. So I'll take this 1 by 1 plus e power W0, W1 x1, W2 x2, like this. This would act as probability, right? And then later with a threshold, threshold 0.7, you will classify it as either 1 or 0. Okay. So now if I ask what is the relation between input features and output feature. Okay. Input features and output feature in logistic regression, what would you say?
Linear.
Yes, this is linear. We have assumed this. It's linear. You are looking at this, I understand, but this is just a transformation. Okay. Initially, it is assumed as linear. You will get some y value that you are taking it and putting it in sigmoid. That is why the final probability graph, this is sigmoid, this is nothing but probability. Probability graph is like this. But this is the relation between probability and inputs, not the actual output that you are predicting from this. The output is assumed to be this way, linear. Okay. That is why but this is not the correct relation, because this will give us the numerical value anything from minus infinity to plus infinity. What we want to do, classification using logistic regression. So we will take this and put it in sigmoid, and we will get somewhere between always 0 to 1, which using threshold we will again classify it. That's how we are converting it into simple volume. So logistic regression is still a linear model. Linear regression is linear model. Logistic regression is also linear model. Okay, now you may get confused. Okay, we have used ANN. In ANN, we have used sigmoid. So now, will you tell ANN is also linear? No, I will not tell that, because ANN is definitely non-linear, because okay, observe the everything you have to observe, so you will know properly. Okay, assume like this. I have this is y hat. Fine. Here I have taken tan h, let's say. Okay, whatever, tan h, sigmoid, whatever I take, no problem, right? So this one I have relations. So y hat is, here I will take some w 3 to 6, so 7, w7, w8 equal to okay, 1 second. Tan h of okay, n11, n12, and n11, you know it, I'll get from these. N12 I'll get from these. You know that, right? So already it is non-linear here, isn't it? Y hat I'm predicting because of this one. The relation between y hat, that is output, and inputs. Inputs will be from here, x1, x2, x3, which is within this. Okay, is already non-linear here, right? Even if I take sigmoid here, what will it be again? Y hat is equal to, oh sorry, this will be here. Okay, this if I take sigmoid, let's say this is sigmoid, because this I'm taking sigmoid, right? If I take sigmoid, okay, so here it is y hat equal to this sigmoid of this, but here in logistic regression it is y hat equal to this. This is linear relation, right? This is what relation?
Yeah, got it.
Non-linear.
Non-linear.
So that transformation is not happening anything here. It is purely non-linear, right? But if you don't take any activation function, then it is linear. I agree. But when we take activation function here, then it is linear, non-linear. Okay. So if somebody asks logistic regression is linear or non-linear model, stick to the basic and tell this. You should understand uh, the intuition of the model, right? Linear model, logistic regression. What is it trying to do? Why is it trying to do? You need to understand. You think everything as a story, then you will remember everything one by one. So like I told, this is a story. In early 1900s, nobody had this ANN models to run, because computers were not very good at that time, right? So people used to do all mathematical tricks. They know linear regression. Regression can be predicted. So people used to predict that regression, linear regression, and that prediction they used to simply transform between 0 to 1, because that will act as probability. Because of probability, you will have a threshold, and you will finally have a classification as output. Okay, right? That is how simply they used to do logistic regression. And which function will transform everything between 0 to 1 is sigmoid. So they use sigmoid. Simple. Okay, there are many other points also in logistic regression. The assumptions are not same as linear regression assumptions, but I don't want to go into all ML now. So let's continue. Okay, so we have understood about the cursor of dimensionality, right? That is main reason why PCA was invented, right? Especially in 1950s, because there was no enough computation power and it is difficult to find non-linear complex models. So people used to transform the data into smaller dimension. When the data is in smaller dimension, the data will be little tightly packed. Variance will be little less. Then a simple model is good enough. Simple model is good enough. Okay. Now using PCA, we will get new dimensions called principal components. New features, new dimensions called principal components, which are linear combination of original features itself. What does it mean? Let's understand. Original data, many input features. Therefore, this suffers from COD problem. What is COD?
Because of dimensionality.
Yeah, good. Suddenly, I thought cash on delivery. So I don't want you also to think like that. So I was just checking. Yeah, so let's reduce the dimensions. For that, we will use basics of linear algebra, guys. Basics of linear algebra. Okay. So what we will try to do is this, the intuition. Intuition, I will tell you, and how we will do, I will be using the mathematics. We will see with the example. So many features, so many dimensions. Data is like this. Curves of dimensionality. Okay. But what if I actually have this line over here? And also this line over here. As let's say dimensions. These two dimensions, if these two are dimensions, okay, is it actually covering the most of the data? Or
Yeah, it is.
let's say it is covering, right? So
Yeah.
it is covering. You just take this outside and transform it. You see, if I take it like this outside and I transform it this way, okay, this is like x-axis, x1 axis, x2 axis, x1, x2 axis. Okay, so I'll just put it back here. You take it and you take it and we turn it just for our representation. I'm just turning it just for our representation. It will be something like this. So just look at this. Just look at this. I have x1, x2, x3 until xn. Let's say 40 dimensions are there. Using these 40 dimensions, this is how the data was represented. Now I am telling, hey, why to have that x1, x2, x3, x4 until x40 dimensions? Why not I have some new dimension called, let's say I will name it as M1 dimension, M2 dimension, some dimension, right? M1, M2, where on these two dimensions, the data is very aptly fit, very aptly captured. Okay, so why not I take these as my dimensions? These as my dimensions. I will have only two dimensions to deal with, right? I have PC1, PC2 dimension, and Y, let's say Y is also here. Y is also here, right? This is the point of Y. So Y to have 40 dimensions, x1, x2, n to x40, I should build a relation which is a function of x1, x2 until x40. If I take these 40 dimensions, okay? But somewhere in the universe, somewhere in the space, there are some two dimensions which actually captures the data like this very well, right? So I can just build a model which is y hat is a function of PC1 dimension, PC2 dimension, which is easy to deal. Easy to deal. Only two dimensions. But what are those two dimensions? How to find? There are many dimensions possible. This could be a dimension, 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 this could be a dimension. Like this, how many dimensions are possible? Infinite are possible, obviously. Right? Among that, how to find this dimensions where actually I get data represented within these 2 dimensions, or maybe sometimes even 3 dimensions, right? We need to know that. So that can be identified using linear algebra topic, eigenvector, eigenmatrix, eigenvector, eigenvalue. Using that, we can identify it. Okay, and it is all about transformation, transforming your data into another dimension, right? Yeah. So, okay. So far, have you understood the intuition? Any conclusion in the intuition? We'll go into the mathematics part next. We need to identify such dimensions, right? Where you will have data like this. On this, you can fit any model you want. On this, I can fit a model like this, or I can fit a model like this, or I can fit a model like this, or I can fit a model like this. But over here, it is much complex. Clear, everyone? Any questions?
Yeah.
Yeah, clear.
Okay, okay,
Clear.
great. Good. Thanks. So here, now, let's see this. This is the formula that will be considered to identify eigenvectors. Okay. And what is this eigenvector? I will tell you how we will use the eigenvector in our PCA model. First, we will understand this eigen vector, how to derive it, and this basic linear algebra concept. Okay, so observe this properly, guys. Observe this. A is a matrix. V is a vector. Lambda is scalar. And then V, same V, okay? Same V is a vector. This is how the formula is. Just imagine this. Always remember with respect to intuition. The intuition or the meaning here, what we will have to understand is, there is a matrix. When it is multiplied with a vector, or you can also consider it as there is a vector which is multiplied with a matrix. Dot product. Matrix dot product. The result is the vector again. But with a different magnitude or scalar. Okay. So when we look at a vector, what are the 2 properties of a vector, guys?
Direction and magnitude.
Correct. Direction, magnitude. Okay. So if I have this is vector in this direction, going on, but magnitude is only this much, right? Magnitude is only this much. This is the direction, magnitude. So usually like this we will represent, right? Vector with direction and magnitude. Correct. So what I'm trying to tell here is, when a vector is taken and dot product with a matrix, I'm getting the same vector again. This vector dot product with a matrix. Matrix is representing, usually matrix means what? You will have a you will have in x1, x2, x3 input features, and you will have values. So it's like a dimension, let's say. It's like a dimensionality space, let's say. Okay, when that is taken and did a dot product with a vector, if you get the same vector again but different scalar means it might increase to this much, like this, or it might decrease to this much, so like this. Okay, magnitude changed, but direction is still same. Okay, that's what we are getting as a result. Fine. Okay. But if you consider one particular matrix, if you consider one matrix like this, and if I do a dot product with a vector, I will get the vector back again, but with a different magnitude, but same direction. Same direction, that's why I took V again, but in a different magnitude. Fine. So how many such vectors will be there, guys? Will there be many vectors or very few vectors like this, which will have this property of this formula? See here, many vectors are there. Many vectors, this is a vector, this is a vector, this is a vector. Many vectors will be there, right? Do you think all the vectors will follow this particular formula for this given matrix?
No.
Very few will be there, right? Which will follow this. Maybe this one is not following. Let us say we'll take one. This one is a vector, but after doing dot product with matrix, it became this. Direction also changed. Magnitude also changed. So this formula is not valid for this vector, but this formula is valid for this vector. Okay, like that in the universe, for this matrix, only few vectors will be there, which will follow the formula, this formula, right? But what does it actually mean is this only, that when this is applied to transformation, you will get the same vector again with different scalar. So let's understand the meaning for that once again. So yeah, so okay, now let's understand this little bit deeper. So you understood what is this representing? What is this representing? Let's understand even more deeper. So matrix into vector is the same vector with different magnitude. What it actually means is whatever information is there in the matrix is also there in the vector. That is why you are getting the result, the vector back again. Okay, but see, the magnitude is changing, right? So when will, okay, so you look at this example, see this, observe this, x into y, not normal arithmetic calculation, guys, normal arithmetic calculation, x into y is lambda into y square. When will this happen? When x is equal to y, yeah, you will get this. Same, you will get y square. But lambda means, okay, there is little bit more, x equal to y into, let's say, 1.1, something like that is there. Right? So some lambda will be there. But the point is, x is having what y is having, and some more information, little bit something is there. Okay? Clear, right? This is simple arithmetic operation. It's clear. Now, if what is the advantage of finding such a y or such a x? Look at this. Look at this. Now now we will look in terms of linear algebra. In linear algebra means we are clearly dealing with what? Vectors, matrices, dot product, transformation, and everything. So I have a matrix. Okay. If I find a vector, where let's say both of them are having similar information, that is why the result is again this vector again, which means lambda a is having v into something, some k or some lambda whatever. That's why you're getting output as lambda into this again. Fine. So it means both are having similar information. Wonderful. So matrix has how many dimensions? Let's say x1, x2, 40 dimensions. Matrix has 40 dimensions. 40 dimensions. Vector has again 40. This is 40 cross 40. This is 40 cross 1. Okay. So which is easy. This is like one dimension actually. Vector is only one this thing, right? One dimension. I mean, if you look at individually, it is like one thing. Matrix is more. So instead of dealing with matrix, we can deal with this vector. Okay, that way we deal with lesser number of dimensions. Right? What I mean is, you have this data, too many features, curse of dimensionality. Now, we have to find the covariance matrix of this data. Covariance matrix of this data. Why? Why covariance? Simple is just understand here again. See, PCA is more about understanding why every step we do. Okay. So here I have many dimensions. Fine. So the variance will be high. If I'm telling these two dimensions are capturing this data, are like representing this data very well, can I say these two dimensions is capturing the variance, everything available here, almost everything available here?
Yeah, we
Because
can say that.
Yes.
correct. If I have 40 dimensions here, there is a lot of variance with 40 dimensions. If any two new dimensions is representing equal to the older 40 dimensions, which means obviously these two should be covering this entire variance or almost the entire variance, right? So I need the new dimensions to be able to have the entire variance of the data available and be there, right? So but that is why I have to take this matrix data points. I have to identify the covariance matrix. Covariance. Okay, where will the variance information of the data be there? In the covariance matrix, right? I have the data. I have Y. Okay. Where is the variance available? In the covariance matrix. Covariance, you understand, everybody knows what is variance, right? Variance is within the variable, right? Variance I have with respect to x1, x2, x3, and also I have with respect to entire data. Entire data I have variance. Covariance is with respect to every two features between this and this, and so on. Okay, covariance matrix. So the covariance between x1 is equal to variance of x1 only, obviously. Covariance of x2 is variance of x2, right? So this will be same, and this will be variance, and everything else will be covariance. I have covariance, which means here in this matrix I have the variance information of the data. This is not the data, guys. This is not the data. Data is here. On that I have applied covariance matrix. I got the covariance representation in this matrix. Okay, this will always be a square matrix. Can you tell why?
Because
on
we are
both sides
we are
same
comparing
features.
it with the same number of input features on both them.
Correct. Yes, it will always be a square matrix, right? And there will be inverse existing for a square matrix always. If I want A inverse, A is a matrix and I want A inverse, A should be a square matrix. So there is always a inverse for this covariance matrix. That is one thing which you should understand. It's a linear algebra property, basic linear algebra property. Great. Now, here I told you in this formula, A is a matrix, right? What matrix is that? That is not the input matrix, guys. That's not the input data. It is the input data's covariance matrix I will be taking. Okay. Which means in A, variance information is there. Variance of the data information is there. That information is available in this vector also. That is why you're getting the vector back again. Exactly like this particular arithmetic formula. Same intuition you can have for linear algebra formula. A is having variance of the entire data information, which is what? M cross M, right? Or N cross N, right? That could be available in a vector N cross 1 or in another vector N cross 1. Let's say like this, two vectors are there which satisfy the formula. Okay. So I can have two vectors and that vectors will be this new data dimension, because these ones are the ones which having the variance information of the entire data, right? So the eigenvector, this is called as eigenvector, by the way. Eigenvector is the vector whose direction does not change, but magnitude may change. May change. That is called as an eigenvector. Why is it eigen? The person who invented this kind of a, or discovered, I would say, discovered this kind of a vector property, it was eigen. His name was eigen something, so he just named it after himself as eigenvectors. Vectors, when done dot product with a matrix, and that result in the vector back again, but with a different magnitude, maybe, are called as eigenvectors. And those are our exact need, right? Where we need to have a newer dimension covering the data variance, right? So what has the variance information? The covariance matrix has the variance information. So let's take the covariance matrix and let's find the eigenvector for the covariance matrix. Let's find the eigenvector for the covariance matrix. Because eigenvector, when multiplied with a matrix, will get the eigenvector back again, but with a different scalar maybe. So those will be our new dimensions. Okay. So what's this? Yeah, this is an example of vector property. Same direction, but different magnitude. Magnitude is different. Okay, that's why we discuss this. Fine. So guys, this is the intuition. Okay. Any questions, any confusion? Is it too much to understand? What do you think? If you look at in a very simple need, what do we need? You just understand what do we need. Accordingly, you can understand why we are dealing with this formula and why we are identifying something called as eigenvector. Right? In universe, there exists a vector called as eigenvector, whose direction will remain same, but magnitude may change when multiplied with this one, matrix, just like this. And this means, and that means, what does it mean of an eigenvector? It means that the eigenvector has information what is there in the matrix itself, almost. Okay, which means whatever covariance information was available in the big matrix is somehow available in a small vector also. Available in a small vector also. So let's take this vector and then use it to transform into a new single dimension. Okay, we will see with example how we will find the dimension also. But so far, is it clear so far?
Yeah, clear.
Okay.
Yes.
Okay, great. Now PCA linear algebra basic. Yeah, let's see this. Guys, just a small mathematical example to identify if a vector is eigenvector or not an eigenvector, right? And when I say eigenvector, it will always be with respect to a matrix only, right? Not independent to anything. If I tell 1, 4, is it an eigenvector? You will tell, okay, tell me for which matrix you want to check. You will do the dot product and then you will check if you are getting the vector back again, right? But with a different scalar maybe. That's what you need. So matrix is given. You need to check if this is eigenvector. How to check? Very simple. We know this is the formula. So let's do A into B. Okay. We got this. 624. Can I express 624 as this? As this. V is what? 1, 4. So I think I can take 6 as common and I can express 1, 4. Therefore, 6 is lambda. This is my initial V. So I can write as lambda dot V. So yes, this is a eigenvector for the matrix A. Okay. Now let's see if this is eigenvector for this matrix. Okay, let's do A dot V. You will get 18, 7. Somehow 18, 7, I cannot convert it into lambda into 3, 4 vector. I cannot convert because if I take 6 as lambda, then 6 into 3 is 13, okay? But 6 into 4, if I take 4, 6 into 4 is 24, which is not 7 years. So it's not working out. I'm not able to express this as lambda into this. Okay, so So this is not an eigenvector, right? For this matrix. Yeah. It's not an eigenvector. Right? But there will be some eigenvector for this matrix. Something will be there, like -1, 2, something will be there. That's we need to find. We need to be able to find it. But it is not possible to find every matrix one by one in a brute force method. So we will have to derive it. So this is how we derive it. This is what we know. Now what people are doing is they are having an identity matrix here just to simplify identity matrix. Because here I have a matrix, here also I will need to have a matrix. So I'll have identity matrix. And then I will take this in this side. I will get equal to 0. And I will take modulus on both the sides. Modulus of this is 0. And this will be, a v is taken out and then thrown this side. So v is gone. So a minus lambda into I is equal to 0. This is what I have. This is what I have. Let's see what happens. So this one I can write like this, right? A is this minus lambda into I. Identity matrix is this. It's equal to 0. Fine. Okay. So I can further simplify this like this. So now simply do the determinant formula. This into this minus this into this. Okay, I'll get this. And you will get lambda. You will get lambda. Okay, so you have lambda. Now substitute lambda in the above equation. What is the above equation? This one. What is it? This one, a into v equal to lambda into v. This one. Okay, I know a, I know lambda. So I not identify v? Yes, you can. So you will substitute it. You will take v as xy, right? And lambda as 6, and you will get this. So you will get v. And again, you will substitute lambda as -7. And again, you will find xy like that. So finally, that is how you will get the vectors. Okay, vectors. Right now, again, let's see how using the eigenvectors, principal components are calculated. So right now, so far, we have seen how eigenvectors are calculated. From that, we will see how principal components are calculated. That is the new dimensions. Okay. Yeah. So guys, just give me, just give me 5 minutes, guys. There is a parcel at my door. I'll be back. Just give me 2 minutes, guys, please. Okay, I'll be back. Wait. Yeah, hey guys, so I'm back. Sorry for the gap, guys. I just had to collect something because otherwise he would again go away. Yeah, okay, so let's continue. Yes, so we have discussed so far that what are eigenvectors, and now and how will we get the eigenvectors, right? How will we get the eigenvectors? How will we get it is simply using this basic linear algebra operations. We know this is the formula. Okay, so we will have an identity matrix in this side so that I can transform it and then do the subtraction and everything. I will transform it I mean, I will take it this side. I will take it this side and I'll subtract it. And I will take V common and that will go this side. So that will be 0 overall. So I'll have this. The determinant of this is equal to 0. So simply take what is A and what is I, and then equate it to 0. You will get two equations. Therefore, you'll get a square polynomial, right? So you will get two lambdas. And for each lambda, you will get a vector, which you will again derive. Okay, that is how usually eigenvectors are found, right? And you need not find the eigenvector. Everything will be done behind the Python code by when you just have to say PCA dot fit. PCA dot fit. That's it. Everything will be calculated internally. Eigenvectors will calculate internally. From eigenvectors, you will get principal components internally, and you will get the new dimensions as a result of the code. But you need to know the mathematics behind the intuition behind. So I told all this. Okay. Yeah. Now let's see how we will get principal components. Okay. So initially, let us say I have 5 dimensions, for example, right? And I want to reduce the number of dimensions for this. Just for example, I'm taking for 5 dimensions, there is no need to reduce. But for example, I want to cover, so I'm taking only 5 dimensions. Usually more than 50, you can go for PCA. That too nowadays not required. Nowadays, it's mostly not required. Okay. So for example, for 5 dimensions, I want to have PCA. I want to reduce to, let's say, 2 or 3 dimensions. What will happen first? First, the covariance of the entire data will be found. Yes, right? So the covariance matrix will be like this. Okay. So for this covariance matrix, I need to identify the eigenvectors. Okay. And how many ever dimensions are there, those many eigenvectors will be there. That is the property. Okay, guys. That is a property because at max from the 5 dimensions, you may again get 5 dimensions only maximum, right? It doesn't make sense to get 6 or 7 more dimensions from 5 dimensions. It will only increase the variance. It'll add noise sort of. So for a given matrix of n cross n dimension, there would be n eigenvectors. Okay, all the eigenvectors will be identified. For example, for this matrix A, and what is A? Is it the data?
No, the covariance of the input.
Data, correct. Yeah. For that, we have identified these as the eigenvectors. 2, 3.4, 24, 3, 7 is the first eigenvector. Okay, this is the first eigenvector. According to that, the principal component, which we have already learnt, which are, it is nothing but the linear combination of original features. Original features linear combination. Now look at this, and we need to understand the meaning also for this. So principal component 1 is 2 into x1, 3.4 into x2, 24 into x3, plus 3 into x4, plus 7 into x5. Where did I get this 2, 3.4, 24, 3, and 7? This eigenvector. This eigenvector, which we have identified from the covariance of the data. Covariance matrix of the data. Okay, fine. I have the first eigenvector. Therefore, I got the first principal component, that is the first new dimension, right? Which means if I have 1, 2, 3, 4, 5, I have identified one dimension, new dimension. But I can have maybe one more dimension, new dimension. Okay. So let's take this V2. Minus 10, 20, 10, minus 23, 3.4, 24, and 6. So I have this here. But as I told, linear combination of original features. So x1, x2, original data, original features given, right? But it is a linear combination of original features. So this is what linear combination only, right? x1 plus x2 plus x3 plus x4, but with some, magnitude. If I have 3.4 x2 power 3, this would be non-linear combination because I have a power 3. Anything greater than power, anything other than power 1. Anything other than power 1 is non-linear. I have everything linear here. This is a linear relationship. Okay, principal component is linear combination of original features. Okay, principal component 2. Now understand the intuition also, guys. See here. I have these dimensions. I'm telling this dimension is derived from linear combination of these dimensions. This, and this linear combination of these dimensions. So will it not cover the variance among all these 5 dimensions in this one single dimension?
Yeah, it will cover.
It will cover because I'm taking all 5. So instead of having 5, let's take everything and combine everything and derive a new thing called, this one. But what is that combination? What is that combination? It should be that combination which will cover the variance of the entire data, right? And that is simply the eigenvector, because eigenvector is in the direction of the variance, right? So you see here, this covariance matrix, right? It will have magnitude and direction. Magnitude and direction, right? It is, if it is going in the same, this is also in the same vector you're getting back, which means the same information is here, and direction is also same, which means the variance direction is covered. So here the variance direction is this way. So first of all, there are 2 directions in which the data is going, guys. So again, this is how a data scientist have to think. All the data scientist thought process should come here. Variance, if you see it, I see a variance in this way, right? There is a variance here, right, between this, like this. And also I see a variance here like this. Yeah, right? So it's one is here, another is here, one is here, another here, like this I see. So variance I'm seeing in 2 ways, this, and I'm not taking straight like this. I'm taking like this because that's what the data is, right? And I'm not taking like this straight. I'm taking a little bit directional, right? So this is how the data is. This is one variance, and this is the another variance, spread. It's spread in like 2 sides approximately. But if I have everything like this, like this, so variance is mostly in one direction only. In this direction, is there any variance, guys?
No.
Not much at all, right? Very less spread. So I no need to have this dimension, unnecessary waste of having another dimension. So it's just enough to have this, right? Like this, similarly, you just observe, I have 5 dimensions, but variance is majorly in these 2 sides only. That's exactly what this principal component 1 identifies. And if the first principal component will be the one which covers the maximum variance. Maximum variance. So between this is the first variance side. This is the second variance side. Which one is having more spread? This one, right?
Yeah, PC1.
Yeah, PC1 is more. Exactly. This is having more spread. So spread is from here to here. But here to here is little less. The spread is less compared to this direction. The spread is more. So that is why PC1 will always be this one only, where the spread is more. In which direction the spread is more. PC2 will be the other one. So every principal component will be linear combination of original features, right? Which is covering the variance, right? Somehow. But that linear combination is derived from eigenvector, because eigenvector is that vector which will cover the covariance. It has the same information as the covariance matrix. Why am I taking covariance only? Why not I take the data here as the data in this formula data? Because I want the dimensions to capture the variance of the data as much as possible. Variance it should capture. That's a spread it should capture very well. That's the whole point, right? That is why I am taking the covariance matrix. Also because covariance matrix will be in n cross n dimension, therefore A inverse will exist. We need A inverse to be able to solve for eigenvector, right? Okay, so that's why we do this. Now you can see principal component 1, principal component 2. Okay, I think that's it. So again, principal component 1, it will be this, like this. Please remember this. Tomorrow I will show you the code also. Right, tomorrow we have, I will show you the code for PCA and maybe one more LSTM code. And then last autoencoder concept. That's it. Tomorrow will be the last class, guys, mostly. And I may extend for 10-15 more minutes because I want to give some more important points. So that will wait. And I'm not sure if I can take XGBoost and other classes because I have to travel to Mumbai for my office purpose. Next 2 days, I have to next 2 days, after 2 days, I need to travel. So my time schedule is little very tight. So I'm not very sure, but I will ask other people to consider and take it. Otherwise, I will check with Abhishek if it is not covered even after 2-3 weeks, then I will take it myself. Right? XGBoost and other boosting technique. It's a huge topic again. It will need 2 classes to finish. Now, yeah, this is how we will get. So yeah, this is the data. This is the original dimension. This is the transformed dimension. Now the data is reduced to 2 dimensions. Okay, now it's not over. Problem is not over. This is just the beginning of building model. Initially, when I have 50 dimensions, let us say, I am not very convenient to build a machine learning model like linear regression. So I applied PCA. I applied PCA and converted into 2 dimensions, let us say. 2 dimensions, let us say. Right? Where I have Y, PC1, PC2 as my data. So on this data, can I build a linear regression model?
Yeah, we can build.
Yes. So I will build a linear regression model on this data. Something like this I will build easily because I have only 2 dimensions. So to build a linear regression model on 50 dimensions, first I need to transform it into 2 dimensions using PCA and then build on this. Okay, that's how I will have to do. Actually, there are 3. Other one is Y, but we will not take it as part of input. So I'm just telling 2. Okay, but again, like I'm telling, if you have 50 dimensions, nobody will apply PCA now. People will have applied definitely A and M, deep learning, right? Okay. Now let me ask you one question. Linear regression is a linear model. Logistic regression is a linear model. ANN with activation functions is a non-linear model. PCA is what?
Linear model.
PCA is
Linear.
linear. Non-linear. Okay. People are telling linear, people are telling non-linear. Tell me reason why. If linear, why? If non-linear, why?
PCA is a linear model according to me because it is actually considering the linear combination of the original features. That's why.
Correct. Exactly. What will PCA give us? Will it give us Y prediction? Y prediction it's not giving. It is giving what? New dimensions it is giving. That's it, right? New dimension. And how is new dimension derived from the old dimension? Using this approach. New dimension are linear combination of original features. It just says in the PCA. So this is how the new dimension is. It's a linear combination. It's a linear model. Simple. If I go for polynomial regression, y hat is w0 plus w1 x square plus w2 x2 power 1.5. This is what y is having non-linear relation with inputs. So it is non-linear model or polynomial regression, right?
Yeah.
Okay. Yeah. This is simply straightforward. In PCA, we are not doing Y prediction. We are only getting new features. On the new features, we can build any model. Linear regression, let's say, where you have y hat is W0 plus W1 PC1 plus W2 PC2. You can have this. It's a linear model, and this is also linear model. So PCA is linear model. So PCA is used for dimensionality reduction. Because why do we have to reduce dimension? Because there is something called curse of dimensionality. What is curse of dimensionality? As you have more features, simply come here. I'll share the notes anyway. More features, but there is more dimension, more variance. So more non-linearity of the data. Therefore, more difficult to capture a model with non-linearity. Right? In 1950s, not now. That's curse of dimensionality. So to deal with that, because of linear algebra basics, it's fully linear algebra, right? PCA is completely mathematics. Completely, it's like 12th class mathematics, 11th and 12th class mathematics. That's it. 11th and 12th class mathematics. You understand why, it will be everything easy. Find the covariance, and for that covariance, find the eigenvectors. That eigenvectors, you take linear combination with respect to the original dimensions. That is the model. Sorry, that is a new dimension. That's it.
Manika.
Simple. Yeah.
So this
Yes.
principal component 1 and principal component 2 is always going to be orthogonal to each other.
Yeah, they will always be, yes.
How
They
the
will always.
okay. How the third principal component would be then?
That will also be orthogonal, just like these 5 dimensions are orthogonal, right? It's difficult to visualize beyond 2, but all will be orthogonal. All will be orthogonal. Yeah, we will see again in tomorrow code. I will show you all this, how actually after the dimension reduction, how we can visualize the data. I will show you that.
Yeah.
Okay. Yes, all right. So let me stop the screen share. Any questions, any doubts, guys?
No, clear to me.
Okay, good. So please observe the thought process, how the data scientist would think. Like most of the time, always you should mostly you should visualize the data and think about variance, because variance is spread of the data, and all we have to do is capture the data, which is capture the spread of the data only, no matter which model you deal with. ANN, RNN, LSTM, CNN, linear decision tree, XGBoost, whatever we do, is we are trying to capture the spread of the data, but not becoming overfit and the trained data. Okay, so variance is that important, right? And logistic regression is linear model. Okay, yeah. So these are the important points, guys. Only one topic is left, which is auto encoder, which is very simple. You can finish it in 15 minutes max. Auto encoder, which is again dimensionality reduction using neural network approach. Okay. Yeah. Okay, that's it. Okay, so that's all, guys, for today's class.
Manika,
If
one
you have-
last question, Manika.
Yeah.
So only principal component analysis is used for dimensionality reduction. LDA and factor analysis, are these important to know?
LDA is also important. No, that is actually not much in the dimension reduction. It is more in topic identifying similar topic level clusters within the data. Topic. It could be like any topic. So
Okay.
if there are few documents talking about sports and few documents talking about politics and few talking about technology, everything is there in one folder, let's say. So you just send it to LDA, it will organize as per the topics. Like few folders will go into one cluster, few files will go into one cluster. Yeah. So it's not dimension reduction because I need to cover auto encoder as a part of it. So I told PCA.
Yeah. And regarding the factor analysis?
Factor analysis is also again same for topic segmentation.
Oh, I see. Okay. Everything is regarding clusters.
Yes.
Okay. Yeah, okay, thank you.
Okay, great. Okay, guys. So tomorrow is the last class. Very important. Please join because I may tell all the summary of what we discussed. Few important bullet points. and you need to make a record of that also. So please join everyone. Don't miss it. Okay. Yeah. Thank you guys. Thank you everyone. See you tomorrow, guys. Bye guys. Bye everyone.